Hi everyone, I am Madam Rosmaya. Welcome to my YouTube channel. I am a pre-U physics teacher at SMJK Yuhua. In this video, we are going to discuss on escape velocity. Imagine how fast would you throw an object that it never came back down. This is where escape velocity comes into the picture. It is the minimum velocity required to escape a planet's gravitational pull. A space leaving the surface of the Earth should be going at a speed of about 11 km per second to enter the outer orbit. So, the escape velocity is the minimum velocity that is required for an object to free itself from the gravitational force exerted by a massive object. How fast a rocket would have to go to leave every planet? It depends on the distance of the object from the massive body and the mass of the massive body. More the mass, it will be higher. Similarly, the closer distance, higher will be the escape velocity. Next, we are going to derive escape velocity. We are going to use principle of conservation of energy. K represent kinetic energy and U represent gravitational potential energy. Total of initial kinetic energy plus gravitational potential energy equals to the total of final kinetic energy plus the gravitational potential energy. At the surface of the Earth, the kinetic energy initial and the gravitational potential energy initial is given by Ki Ui. And at the point where it is at the outer space, the kinetic energy final and the gravitational potential energy final is given by Kf and Uf. So therefore, Ki plus Ui equals to Kf plus Uf. Uf, gravitational potential energy final, is 0 as the distance is infinity. And kinetic energy final will also be 0 as final velocity will be 0. So Ki equals to negative Ui. So we bring Ui into the right side, become negative. K is equals to half mv squared. So we substitute escape velocity into v. So we get half mve squared. Gravitational potential energy is given by negative gmm per r. So initially, the rocket is on the surface of the Earth, so we can put as gmm per capital letter R for on the surface of the Earth. Negative and negative become positive. And we cancel out the m, mass of the rocket. So therefore, the escape velocity equals to square root of gm per r, where g is the gravitational constant, m is the mass of the planet, and r is the radius of the planet. We can also use the relation between mg equals to gmm per r squared on the surface of the Earth. And we can cancel out m both sides, so we get cross multiply, so we get gr squared equals to gm. So we substitute into the equation here, we get square root of 2 gr squared per r, cancel one of the r, so the answer is square root of 2 gr. Here we notice that the relation is independent of the mass of the object, which will be escaping from the massive body. So escape velocity are given by these two equation. Since escape velocity depends on the mass of the planet or moon from which a spacecraft is blasting, a spacecraft leaving the moon's surface could go slower than one blasting off from the Earth because the moon has less gravity than the Earth. Next, we are going to find the velocity for the rocket to be launched from the surface of the Earth so that it will not fall back to the Earth. If we use this equation, escape velocity equals to square root of 2 gm per hour. So we substitute the value of gravitational constant 6.67 times 10 to the power of negative 11, and mass of the Earth is 6 times 10 to the power of 24, and radius of the Earth is 6.4 times 10 to the power of 6. So the answer we get 11 kilometer per second. If we use the second equation, escape velocity equals to square root of 2 gr. So square root of 2 times 9.81, the value of g, acceleration due to gravity, and the radius of the Earth is 6.4 times 10 to the power of 6. So we also get 11 kilometer per second. We are going to determine the escape velocity for Sun using the equation square root of 2 gm per hour. So we substitute the gravitational constant 6.67 times 10 to the power of negative 11, and the mass of the Sun is 2.0 times 10 to the power of 30 divided by radius of the Sun 7.0 times 10 to the power of 8. So the answer is 620 kilometer per second, which is larger than the escape velocity of the Earth. This explains why hydrogen atoms fail to escape from the Sun. So the escape velocity decreases as the distance increases. The escape velocity is lower at greater heights above the planet's surface. The planet's gravity has a weaker hold on the molecules at the top of the atmosphere than those close to the surface. So, those high up molecules will be the first to evaporate away. The thickness of a planet's atmosphere depends on the planet's gravity and the temperature of the atmosphere. A planet with weaker gravity does not have as strong a hold on the molecules that make up its atmosphere as a planet with stronger gravity. The gas molecules will be more likely to escape the planet's gravity. On the surface of the Earth, if the escape velocity is large enough, for example, for Earth, where the rocket is launched at 11 km per second, so it managed to escape the gravitational pull of the Earth. So as it go further from the center, let's say at this point, here the smaller the escape velocity, and at the very far distance at the outer space, the rocket only need a very small escape velocity for it to escape the gravitational pull of the Earth. If the speed of the rocket launch is smaller than the escape velocity, so the rocket will fall back to the Earth. But if the speed of the rocket launch is greater than the escape velocity, it managed to escape the planet's gravitational pull of the planet. To so to for the escape velocity to be achieved faster, so we use a multi-stage rocket instead. So the empty fuel container is ejected to reduce the weight. And another advantages for using multi-stage rocket is it saves the fuel. A rocket fired vertically at a velocity of 11 km per second will escape the Earth. If it is instead launched horizontally at the same velocity and it doesn't hit mountains or other obstruction and air resistance can be neglected, will it still escape the Earth? Refer to the diagram here. One rocket is launched vertically and another rocket is launched horizontally. So, will the rocket still escape the Earth? The answer is yes. No matter how the rocket is launched, whether horizontally or vertically, if it is launched at a escape velocity at a velocity larger than 11 km per second, it will manage to escape the gravitational pull of the Earth. Okay, that's all for the video, the end, and thank you for watching. And don't forget to subscribe my video.